Hello viewers, thank you for coming back. We'll be continuing our next hands-on, which is part of our certification hands-on course, data designing and implementing a data science solution on Azure. We'll be continuing with the next hands-on, which is explore differential privacy. What is differential privacy? Okay, so what is differential privacy? Differential privacy is where we put some noise in the data or the observation which contains some sensitive information, right? So we want to mitigate the privacy issues with the data that we have. Okay, now we add some noise. Through adding the noise, what it does, it will not change our statistical measurement, okay, and aggregation. This will remain consistent for our model, but within the raw source data, adding the noise will help us to mitigate the issue with identifying the values of individual observation, right? Okay, there is one more documentation here or link. So this is a SmartNoise site. Basically, a SmartNoise package will be used within our Azure machine learning experiment. What it does, this SmartNoise is a toolkit which uses state-of-the-art differential privacy technique, okay, to inject noise into the data. Now, by injecting the noise into the data, we can prevent the disclosure of sensitive information and manage exposure risk of the data. Okay, so that's what we will do next. Okay, so I've opened my notebook for that. Okay, and yeah, let's go to this right up here. A machine learning project typically involves an iterative process of data analysis in order to gain insight into the data, right, and determine which variables are most likely to help build predictive models. Okay, so we'll identify which variables are most likely correlated to predict our model, right? Analyzing data usually involves aggregative and statistical functions that provide insight into the statistical distribution of variables and relationship between them. Okay, with large volumes of data, the aggregation provides a level of abstraction. Okay, when we have a large volume of data, aggregation will provide a level of abstraction, but with a smaller amount of data or with repeated analysis, even aggregated results may reveal details about individual observation. Okay, so to mitigate those issues that is highlighted here, right, we use a differential privacy technique. Okay, here we introduce noise to our data, and the goal is to ensure that enough noise is added to provide privacy for individual values, while still ensuring that the overall statistical makeup of the data remains consistent. Overall aggregation or the statistics of the data will still be consistent, and aggregation produces statistically similar results as when used with the original raw data. Okay, so this will produce the same result what we will have with our raw data when there is no noise. So this is just to introduce privacy within our data. Okay, plain and simple. Okay, now a SmartNoise toolkit I mentioned is from OpenDP, a joint project between researchers at Microsoft, Harvard University, and other contributors that aim to provide building blocks for using differential privacy in data analysis and machine learning projects. This is a project between Microsoft and Harvard University. Okay, I showed you here, right? This one. Okay, you can visit this path and learn more about this is SmartNoise. Let's take it. Now we are going to see if this is installed. Okay, Here we are going to install the SmartNoise Python st package. Okay, so let's run it. With this package, once it is installed, we are going to use this package or SDK package to introduce the noise within our data. Okay, you can ignore all these errors for now. Now we are going to load the data with as a pandas library, or sorry, pandas data frame. Okay, so we are utilizing pandas package or library, you can say, and then we are importing the CSV data, right, as a pandas data frame. Let's run that. Here you can see the pandas data frame imported, and it is describing how the data is looking like, okay, for each of the patient. This is our raw data. Currently there is no noise, right? The output from the code above shows the key summary statistics for the variables in the diagnostic data set, right? Now you can use a SmartNoise to create an analysis in which noise is added to the source data. Source data is this raw data. The underlying mathematics of how the noise is added can be quite complex, but SmartNoise takes care of most of the details for you. However, there are a few concepts it's useful to be aware of. Okay, so these are some write-ups. Upper and lower bounds. Clamping is used to set upper and lower bounds on values for a variable. This is required to ensure that the noise generated by SmartNoise is consistent with the expected distribution of the original data. Okay, so it will keep the upper and lower bound of the noised data similar to what we have in original data. So upper and lower bounds of our original data are similar data, or similar data from the noise will be generated. Okay, noise data will be generated with that similar kind of upper and lower bound. Okay, sample size. To generate consistent differentially private data for some aggregations, SmartNoise needs to know the size of the data sample to be generated. So the sample size we have to mention, like how much data it is going to generate. Okay, epsilon. Put simplistically, epsilon is a non-negative value. Okay, it ranges from 0 and 1 that provides an inverse measure of the amount of noise added to the data. It's inversely proportional. Okay, low epsilon results in data set with a greater level of privacy. The lower the value of the epsilon, you will have higher value of, or higher level of privacy within your data, and higher the value of epsilon will result in lower privacy in your generated data. Okay, in your data set. Okay, generally you should use epsilon value between 0 and 1. Okay, epsilon is correlated with another value named delta that indicates the probability that a report generation or generated by an analysis is not fully private. Okay, so delta is a probabilistic variable which it reports, it shows whether a report which is generated is fully private, partially private, or the original data, right? I mean, it doesn't have any privacy within our original data. Yeah, with these concepts in mind, examine and run the following code. Okay, which creates an analysis and reports the mean age value from the differentially private data. Now age is somewhat a sensitive information, right? And we want to introduce privacy by adding some noise to the age value. Okay. Now to do the differential privacy for that age, the actual mean value from the original raw data is also shown for comparison. Okay. So that is also shown for comparison. Now let's run that. So here we are mentioning all the columns of the diabetes. Then we are checking age range is between 0 to 120 years. Samples we are taking from the same diabetes data, okay, with SM dot analysis as analysis. Okay, this is noise, SmartNoise, okay, package from OpenDP SmartNoise.core package or from SmartNoise SDK. Okay, from where we are importing the SmartNoise package and then using a SmartNoise analysis, putting the data set, right, then converting the age upper and lower bounds, right? These are upper and lower bounds of the age. So here we are converting age to float and then get mean of the age. And based on mean of the age, we are trying to introduce the noise, a smart noise. So it's going to create a smart noise with these values. Data of our age, privacy uses epsilon is 0.5, that means neither fully private nor fully original data. It will have 50%. 0.5 indicates the privacy will be introduced up to 50%, not fully private. Okay, and lower age bound and upper age bound we are setting here, and data rows of the samples we are setting here. So all these three parameters we have introduced here, right? Upper and lower bounds, sample size, and then epsilon value, okay, which is nothing but a privacy uses. Then we are running this to create the smart noise. So private average mean is 30.12 while the actual mean age is 30.13. It shows that after introducing the smart noise, still we have the mean age same as what we had in our original data, right? So it is not affecting our statistics basically. That's what the whole purpose of introducing the noise is. It will just affect the privacy and not the data or the outcome of our experiment. Okay. Explore data distribution with histogram. So here we are going to plot a histogram and explore the data distribution. So let's run that, printing the age and frequency true age distribution. Okay, so this is true age distribution from our original data. Okay, so this is age range from diabetes data set. We are taking the age and printing the age distribution. Okay, now let's compare that a differentially private histogram of age. And since we introduced a smart noise, so now we have introduced privacy to our age field, but then again we want to see if the distribution changed, right? Within our age distribution changed within our original data and in the noise included data, right? So let's check that as well. And if you see here the comparison, this very slight or no change in the private data, right? So it has introduced the privacy but without affecting our statistics. If you can see, these are almost same. So we have seen that the histograms are similar enough to ensure that reports based on the differentiality or differentially private data provide the same insight as reports from the raw data, right? So it is not affecting our statistics anyway, right? Now calculating covariance. Another common goal of analysis is to establish the relationship between variables, right? SmartNoise provides a differentially private covariance function that can help with this. Okay. SmartNoise analysis. SmartNoise data set is from the same columns that we had for diabetes. Data path. Okay. Age, BP, COV scalar. I don't know what this variable is, but here what it is doing from BP covariance. Okay, it's taking that function which is part of a SmartNoise, and where we are putting left, right, okay, age, and diastolic blood pressure. Privacy usage is 1.0, that means maximum privacy. Left lower, left upper, left rows, okay, left right lower, right upper, right rows. So using this covariance, differentially private covariance. Okay, so we are just calculating the covariance. So let's check that covariance value. Okay. Age and blood pressure covariance. Okay, this is trying to calculate age and blood pressure covariance. Okay, and we are passing these two values for age and blood pressure. So left and right. Now let's print. So this is differentially private covariance 10.8 and actual covariance is 8.7. In this case, the covariance between age and blood pressure is positive, indicating that older patients tend to have higher blood pressure. So using these covariance values, you can check, right, whether one variable or one parameter is affecting the second parameter. That means with the age, people tend to get high blood pressure. Okay, that's what it is indicating. Next, use SQL queries. In addition to analysis functionality, SmartNoise enables you to use SQL queries against data sources to retrieve differentially private aggregated results. Wow. So we can also use SQL queries as well onto our data to run some data analysis and get the differentially private aggregated results. Okay. First, you need to define the metadata for tables in your data schema. You can do this in a YAML file. Okay. YAML file, we can use that, such as diabetes.yaml. Okay. File in the metadata folder. Okay. It's saying that we'll find this in a metadata folder. Let me open that file. So this is our schema model database, diabetes. Within diabetes database, we have diabetes of patient with 10,000 rows, and each row will have these attributes, right? And their type, lower and upper value is also mentioned. Next, so this is just defining a table data schema. Okay. Now the metadata describes the fields in the tables, including data type and maximum and minimum values of for the numeric fields that we have already shown you. I have already shown you here. Next, let's run this. So it will print that metadata. This is the same thing that we have here, but printed in a collection. collection set. Okay, and with the metadata defined, you can create readers that you can query. So we are creating a pandas reader to read the raw data from pandas data frame. Okay, so we can use a SQL like queries to query the pandas reader. Okay, and this pandas reader will contain the raw data from the data frame. Now, with the metadata defined, you can create readers that you can query. In the following example, we will create a pandas reader to read the raw data from a pandas data frame and a private reader that adds a differential privacy layer to the pandas reader. So we'll create pandas reader and private reader. Okay. Both. Pandas reader will give a raw data from data frame and then a private reader on top of that to add a privacy layer. Okay. So both of these are part of OpenDP SmartNoise SQL package. From there, we are creating both pandas reader and private reader. Okay. Now, for the reader of panda, we need diabetes data and the meta. Meta is nothing but our table structure or the schema, right? And then for private reader, we need this data reader or raw data. Then metadata is again the metadata schema, right? Table schema, and epsilon per column, like how much privacy we want to introduce is 0.7. So the higher the epsilon, lower the privacy. It's inversely proportional, right? So it's more than 0.5, so it is lowering the privacy. Okay, or lowest privacy it is introducing. Okay, so let's run this, and readers are ready. Now we will run the query on top of our result. Okay, private reader. Okay, on the private reader we have an execute query method. So we will pass this query. Select diabetic patient with average age. Okay, and the average age as average age from diabetes. So from this database, this table, you find out all the diabetic patient with this average age. So it's grouping by diabetic patients, right, over this column. Okay, non-aggregated column. So let's run this. We see these two fields and their respective values. False is this and true this. So this is just giving us aggregated result set. Okay, next let's compare the result to the same aggregation from raw data. Now over the raw data reader, right, or pandas reader, we are executing the same query and we print the same set of aggregated results set, right? And if you see here, these are the same result. 0 indicating false, 1 indicating true, but in both the cases, even the aggregated result is also not changing. So that's how we are introducing the noise without affecting the privacy. You can customize the behavior of a private reader with epsilon per column parameter. So it's going to introduce privacy per column, okay, with epsilon per column parameter. So let's try a reader with a high epsilon or low privacy value and another with a low epsilon with high privacy value. That's because we have a inversely proportional relation here. So private reader with high epsilon 5.0 and then low epsilon 0.1. Okay, so here what we see, the epsilon values also increase, not and epsilon value is not only ranging from 0 to 1, it's also increasing like up to 5.0. So any positive value from 0 to any positive value, right, we can put as a epsilon value. So it is introducing a low privacy with a high epsilon value and high privacy with a low epsilon value. Okay, so let's run this, and here we can see the aggregated results. Note that the results of the high epsilon or low privacy readers are closer to the true results from the new raw data than the results from the low epsilon high privacy reader. The result of high epsilon, this is the result of high epsilon readers are closer to the true results. These two are more closer. Note that the result of the high epsilon or low privacy reader are closer to the true results from the raw data than the results from the low epsilon high privacy reader. Okay. So when we introduce epsilon per column, okay, onto the private reader, so we'll see these two values converge to one another. So that's about introducing the noise within our data without affecting its statistics, but only introducing the privacy. Okay, so that's it for now. Thank you for watching. Please like and subscribe my videos if it is helping you out in any way. Thank you. Bye bye.